Oh, hey, it's official. Welcome back, everyone. So we are just 5 weeks away from being done with the semester. But any questions or comments folks would like to start us out with? Okay, well, we're nearly there, and the next couple weeks are pretty pivotal. We have our third exam that's coming up. I'm thinking this exam is going to go up to nothing beyond chapter 4, but I'll have a better idea of the exact coverage depending on how the pacing goes. This is an optimization section, which is application, so I don't necessarily want to throw too much on top of the exam. That one might be the last one for the third exam. And I'll start posting the typical things you expect, the exact coverage, that kind of stuff, review material, as we get closer and closer to the weekend. That'll start appearing. Aside from the exam, we also have our next upcoming quiz due on Wednesday. And this one's based off the closed interval method in section 4.1. And whether you're in section 4.1, 4.2, 4.4, most of the methods start off just like this, find your critical numbers. So that's a good reminder as really a good test taking strategy. If you solve this right here, you're most likely on the right track. The only exception is if the question is about concavity and nothing else, you would set the second derivative equal to 0 and solve, but same general kind of idea. Well, any other questions, folks, before we go back to our section 4.2? Okay, 4.2 is a pretty long section. We have two major things we're looking in there: local minimums and maximums and inflection points. And whether the question is mins and maxes or inflection points, the process is pretty much the same. And I mentioned here in blue that 4.4, I only have 4 problems on there, but they're pretty large problems. All of them are essentially based off the things you're doing right here. We change the methods a little bit, extend on some of them, but it's the same kind of general idea. You're still setting a derivative equal to 0, determining which test you're using, first derivative test or second derivative test, and then optimizing based off that. So with that all in mind, we're now on example 3. And this one is really long as a problem. This would be like 3 exam questions or maybe even 3 different quizzes. But as an overall process of taking a look at everything, it's a great one for the sake of review. The function's also tricky. We have a product rule combined with the chain rule combined with the natural logarithm. So lots of things to practice up in here. And here's how it starts. Here's our f of x function. Let me see if we can zoom in just a touch. First thing we want is intervals where f is increasing and where it's decreasing. But the major thing that we do that for is just to find local minimums and maximums. So part A is a ton of work, and B is like the conclusion to everything you did in part A. First thing we have to do is find a critical number. That's always the first step. Let's write this out as a sequence of steps within part A. We have to solve f prime of x set equal to 0, which means really our first thing to do is differentiate this function here. It's a product rule, so let's go carefully and methodically with it. F prime of x is going to be first the derivative of x, and you can put a 1 right down there, like at this point, if you feel like you've got really great practice with product rule. I'll just do this mainly for the sake of the notes at this point. It'll multiply natural log x squared and go plus, copy your x, and then here, go parenthesis, another parenthesis, natural log x to power 2 prime. So we have a derivative here set up. Now we're ready for the product rule. On this one, we are dealing with the chain rule where the 2 is going to be the outer function we handle second. And natural log x will be the inner function we handle second. So on our next line, we've got a 1 right here. So I'll put in a 1 just to show we did it. There's 1 times natural log x squared, then x. And over here, we start to use the chain rule. Do the outer function first. This will be multiplied by a power 2. The new power is a 1. I'll just put it there just to show the process. Then we multiply by the derivative of whichever function is designated as inner, which is natural log x. So that'll go in both of these spots here and here. So we're nearly done with the product rule. Next thing to do is just start cleaning this up. So right here, we have natural log x to the power of 2. Over here, I'll just write this in as a plus 2x. Then natural log x. I guess we don't need parentheses here. Let's maybe make it look a little bit nicer and drop those parentheses. Next, derivative of the natural log x here is just going to turn into a 1 over x. That's nice because that means we've got this x canceling with that 1 over x to simplify the problem even more. So now, all said and done, we have natural log of x to power 2 plus 2 natural log x. That's not so bad as a derivative. It's in a pretty nice simplified form. Before we do anything further to it, any questions at all, folks, getting to this stage? Okay. Well, again, we said that that's a nice simplified answer, but we also have to remember our objective is to find a critical number, which means we're setting something equal to 0 and solving it. And whenever you're solving that kind of equation, factoring is always a great idea. That means on this line, we should factor this even further than it's shown, or it's not factored at all really, so let's factor it. There's a greatest common factor of natural log x, so we can say that this is equal to natural log x factors out, leaving behind just a natural log x plus 2. And you can visually double check that every time you do this. Here to here would be natural log x squared, so that's power 2. Here to here would be 2 natural log x. That's what we have here. And so our factorization looks correct. Now finally, we're going to set that equal to 0 and solve. Let's do it way B over here. Let's also call this step 2. In step 1, all we did was calculate the derivative, put it in a nice format. In step 2, we're going directly for that critical number. F prime of x equals 0 means natural x times natural log x plus 2 is 0. This has just been a whole bunch of copying. But now at this stage, we're making some headway. This splits into 2 equations. Natural log x equals 0 is 1. Or natural log x plus 2 equals 0. That one's the other. So nearly there, folks. We just have, well, 2 equations now to solve. This one's pretty fast. Anyone happen to know the solution to this one? While we're thinking about it, let's also plot that one just to get a feel for it. Because we're dealing with a natural logarithm, it's actually not a bad idea to plot that portion right there. Y equals natural log x. So here's our logarithm graph. And the reason that plot is kind of helpful is, well, it'll help solve this equation, but also it tells us there is a domain condition on this one. We have to have x greater than 0 in this entire problem because of the natural log right there. You can't even put a 0. But also it tells us even more. The solution to this is right here. Oh, if I can get that to settle. There we go. 0 is the y coordinate, and 1 is the input that gets us to that. So it's automatically a 1. But here's a better way to think about it. I mean, I shouldn't say better way. This is just as valid, and this works for any logarithm. Input a 1 and you always get 0. But if you like working analytically, you might have said that natural log x is log base e of x, and this is set to 0. Now, this is an equation in logarithmic form. You can put it in exponential form by taking e. The input to the exponential was the output to the logarithm, so we switch inputs and outputs because they're inverse functions. And it's set equal to x. X is now the output. And so here's a nice way to solve the equation if you prefer working analytically, just with the equations. Switch input and output and go to your exponential form. Still, we have to know e to the power of 0 is a 1, but we're more used to seeing that, I think. Any exponent other than, any base other than 0 to the power of 0 results in 1. So 1 equals x on that equation. Well, that was so fun. We come up here and just redo the whole thing. Well, this one's a little bit different. If you're going to solve this equation, you want to isolate your logarithm, so subtract 2 from both sides. Natural log x now equals -2. And this would be a good one to use the method right here. Let's put this in a more explicit logarithmic form. We need to display the base to the natural log. It's really log to the base of Euler's number, e, of x equals -2. Then we come down here, change it from a logarithmic equation to an exponential one. So it'll be e to the power of -2 equals x. And if you like arrows, here's the arrows on this one. Inputs and outputs always change if you go from a logarithm to an exponential function or vice versa. The only reason that works is these are a pair of inverse functions. So just to summarize, here's what we found. Oh, let me fix that. The critical numbers are 1 and e power -2. We still haven't gotten to this portion, but we're now really close because finding intervals of increase and intervals of decrease is more about find where the derivative is 0 to begin with, and then just look at the sign of the derivative across those critical numbers. Sometimes called cut points instead of critical numbers in this kind of context. So next thing we do is, if you're thinking of cut points, that's not a bad analogy since we really are cutting up the real number line. But let me pause on here. I don't like the way I drew that number line because remember there's a domain condition. X can't even be negative. So just so we don't make a silly mistake, let's put in that domain condition like this. I'll keep that in purple just to tie together that's where that came from, the fact that we had a natural logarithm. So we're going from 0 to infinity. Now the next problem I have is I don't know the magnitude or the size of e power -2 very well. I just don't think about those numbers often. So what I would do next is grab a calculator and put in e to the power of -2, just to get a feel for it. You don't need a lot of digits. I'd say to the nearest hundredth does a overwhelmingly good job. That's about a 0.14. So this one is about a 0.14. So I'll put the e power -2 kind of close to 0. I'm not trying to get this extremely accurately placed, just well enough so that things are arranged in an organized way. Next critical number at 1, I'll put clear over here. And now we have three different regions we have to analyze. These two finite regions, and then this infinitely long region. They're all going to be relative to the derivative, f prime. So let's use a different color here. Now, next step, we have to find the test values in here, here, and here to place. That's why we needed a temporary approximation of e power -2. I just wouldn't know what to grab unless I knew it's about magnitude. If it's about 0.14, a decent test number would be just a 0.1. That ought to do the job. Over here, we can make this one be, say, a 0.5. And for the last region, I'll throw a 2 there. Notice that my scale is imperfect, but again, as long as 2 is on the right side of 1, it's okay. The scale doesn't have to be perfectly represented. Well, any questions, folks, with what we've got so far? Okay, and I forgot the sequence of steps. I would consider this step 3 of part A of the problem. So when it said the critical numbers are these two, first thing we did was we put them on the scale, found the test values, and now we're just going to, well, literally test them out. This is relative to the derivative f prime, like we indicate on the number chart. F prime of 0.1. I think it's easiest to input it right here into its factored form. Natural log 0.1 times natural log 0.1 plus 2. We don't care to know the exact number on this. We just want to know if it's positive or negative. So back to the calculator. Natural log 0.1 is a negative value. Then it's multiplied by natural log 0.1. plus 2. And that plus 2 was enough to convert all of this into a positive quantity. So we'll just write here, excuse me, greater than 0. That means in this region where we selected the point 1, this is greater than 0. And then it further means, let's put down a small little statement here. That's as small as it gets. We're increasing in that range, only because the first derivative was positive. Now, we are anticipating a sign change, but that's not always so easy to track. We did look at a shorthand on that, but the careful thing would be to just to take the 0.5 and do it again. F prime at 0.5 means we're doing natural log 0.5, natural log 0.5 plus 2. So let's find the size of this thing. If you put this in the calculator once, hit like second enter or whatever the shortcut key is on your calculator, and just go over here and change these to 0.5. That's a good little fast shortcut sometimes in these kinds of things. Here we come up with a negative quantity. So this one is negative, which is probably what you would expect. If it's positive here, and there's no power 2 on any of these factors, this should go to negative, the sign should change, and this one should go to positive. But doing it one last time, this is like a check in the problem so far. So let's see if we're consistent and we really get a positive value. So over here, that's natural log 2. That'll be natural log 2 plus 2. But you know what? This is one you might not even have to put it in the calculator. You went back to the plot, y equals natural log x. Notice that if you're putting in a 2, you're getting positive quantities at about magnitude 0.72. So this is a positive number, and this one's a positive number as well. There's just no chance for anything to be negative here. Logarithms only go negative if you put in something less than this value right here at 1. Then you're getting negative quantities like that, negative 0.5 and so on. So here, yeah, that's definitely positive without even calculating it, just thinking of the graph. So positive here, and I forgot the descriptions. We went increasing, then to decreasing, then back to increasing. So finally, to summarize, we want the intervals where f is increasing and where it's decreasing. That's our step 4, just giving the overall conclusion. We can say f is increasing on this interval from 0 to e to the power negative 2. That's where the sign is positive, and as well, so let's say union 1 off to infinity. Then add f is decreasing on e power negative 2, comma 1. We did it, folks. That's the increasing decreasing test. Again, that's pretty interesting knowledge already, but the major reason why we would do this increasing decreasing test is because what we really cared about was the local minimums and maximums. So part B is like the overall conclusion to part A. Any questions at all, folks, with this full analysis? Okay, well, let's go down below and do it again well, summarize for part B, and then we'll do it all over again for concavity. So part B says state the local minimum and maximum values. I often draw these on the paper since it just kind of makes sense. If to the left we were increasing and to the right we were decreasing, the graph right around e power negative 2 would look like this. But then it decreases and switches to increasing. I don't know what the graph really looks like. I'm just drawing something to organize my thoughts. So I'll delete this in a moment. But right there, that looks like a local maximum. And right there, that looks like a local minimum. But we want the local minimum, maximum values of f, so we still have to do a function evaluation. Let's grab that original function f and stow it away down here. There we go. So we'll say the local maximum is f evaluated at that quantity, e power negative 2, at feel like we need to avoid the page break on this one. Let me just drop it down. Now, f at e power negative 2 means we're putting e power negative 2 here. And in the logarithm, which is squared. Now, because it's a natural logarithm with a base exponential input, these two cancel out, and you're just taking negative 2 to the power of 2. And so this is e power negative 2, negative 2 to the power of 2, which is 4. And so it's 4 e power negative 2. That one is our local maximum. Well, any questions, folks, with finding that first value? Okay, well, let's try it again. There is a local minimum when we put in 1 inside the function. And so we can say next, the local min is f at, grab that critical number 1, then plug the critical number 1 back down inside here. It'll be 1 times the natural logarithm of 1 to the power of 2. But this seems to come up a lot in math classes. I think it's because it's some of the nicer to evaluate logarithms. Natural log of 1 just goes to a 0. That means this whole thing is 0 for the local minimum. Well, we did it, folks. That's the end of our part B on there. Part B is always kind of nice. And if it's a concavity situation, the follow-up part to that is also the nicer part as well. Hope that looked weird. There we go. What I would do immediately after doing this, in particular, not just for web assignment, for quizzes as well, we should just check this out, see if it really looks about right. So let's put in the original function this time, that one down there. So it'll be f of x equals x, natural log of x to the power of 2. Now let's see just how close we got. We claimed that the local max is that figure. You could just throw this in, 4 e power negative 2. It should be about 0.54. Now looking at the graph, let's see, yeah, about 0.54. And the critical number, e power negative 2, we did estimate to about 0.14. So all that looks consistent based off what we said. We really have a local max. And we said the local min is 0, which occurs when x is 1. And that's why we see a 1, 0. So it looks about right, folks. Next thing we're going to take a look at is concavity issues. Any questions at all at the moment? Yeah.
So how did you think about that natural log of negative 2?
This one right here? Oh, gotcha. That one came out from this property right here of logarithms. If you take a log base b to a b power of x, then there's always a cancellation that goes this way, leaving up the x. It just looks really weird though, because it's not exhibiting the base, but down here we're really dealing with log base e of b power negative 2, canceling off and just leaving behind that negative 2 in that position. Other questions about that so far? Or other issues so at the moment? Okay, well, let's keep on going. We've got the next thing to take a look at is concavity. Now, if you already checked your answer, really good idea to look at this graph again, because you can kind of think about where the concavity is. For example, this is just a temporary annotation, but if we put a tangent line, just a horizontal one, it's the easiest to plot, right here, and another horizontal tangent line right here, then we can say in this region, this is concave. Well, let's think about it. Concave down means the curve lies below all of its tangent lines. So that looks like concave down. Concave up would mean the curve lies above its tangent lines. So that would be concave up. In some region right here, I don't know exactly. It's actually pretty hard to just eyeball it and get concavity. So with this already, anything we do down here algebraically, we at least have a good set of expectations of what should happen. Let's take that as a screenshot and just see if it does in fact happen. and also because we have to eliminate the annotation at some point. We'll just squeeze it away there for the moment. And now we're going to start the process all over again with concavity. But to do all that, you need the function the original function, so the f of x1. You also need the first derivative. So let's indicate this down below. We calculate a first derivative to be f prime of x. Let's decide on which version we want to grab. I actually want to grab the factored version right here. This is good if you're doing ordinary algebra. If you're differentiating further, that's a product rule out of nowhere. It's easier to differentiate this one with the chain rule. So all of these are cross equality are f prime of x. And I think for me personally, this would be the easiest one to differentiate right here. So let's drop it down. F prime of x equals natural log x to the power of 2 plus 2 natural log x. Okay, we're done with that screenshot. And if we're doing now concavity, I would consider this to be the best step one. You now need to immediately go and calculate f double prime of x. Now this is a chain rule, but if you look up on the notes, we already did this one as a chain rule once already. So we don't necessarily have to reinvent the wheel. What happened was this power of 2, well, that mouse would stay still, came down. We multiplied by natural log x, then we multiplied by the derivative of natural log x, which is a 1 over x. Again, that's always good to look to your problem. If you notice you're about to do the same chain rule all over again, just cite what you did up above and reuse that. Or if you did calculate it again, you could just double check if we made a mistake on one or the other. So that's the derivative of this term. Then we go plus 2 times derivative of natural log x, which is another 1 over x. And that's our second derivative. Like before, we want to simplify it as much as we feasibly can for the purpose of solving an equation where f double prime of x will be set equal to 0. But notice these both have denominators of x, which means they have a common denominator. So you can start by saying that this is something divided by x. That something would just be the addition of the numerators, 2 natural log x plus 2. I think that's about as simple as you can make this derivative. You could maybe factor out a 2, but it's not really giving you too much. So that's going to be really a personal choice, I'd say. I'd probably just leave it in that format. So we've got our second derivative. The next thing you immediately want to do is take your second derivative, f double prime of x, set it to 0 and solve. This is just like the critical number step, but it's not the critical number for f this time. That's a critical number for f prime instead, since the derivative is 1 higher. Now, the only way that this could ever potentially be true, because we're looking at a fraction, is if the numerator goes to 0. So this implies 2 natural log x plus 2 equals 0. In fact, if you set this equal to 0, your first step is to just multiply both sides by x. You're feeding x to 0. It's just gone from the whole process. And so that's where we're going to start looking. Another thing you might have noticed, though, is that what about when x is 0? That's a critical number in the sense that when x is 0, the second derivative itself just does not exist. But this is eliminated because recall, from way up here, you can't even put 0 into the problem. X must be a positive value. And so if you're looking for issues where the derivative did not exist, the second derivative, well, it did come up, but it's outside the domain, so we're lucky on that one. I think I do not assign too many problems that have those weird technical issues, but it's in there in the definition, just for full completeness. Back to solving this one, we just want to isolate the natural logarithm. So we'll say natural log x equals, subtract 2 and divide by 2, and it's a -1. You can convert this to log base e of x equals -1. Then next, turn it into its exponential form. e to the power of -1 equals x, where same kind of swapping like this occurs. And now we've done it. This is the critical number, which means it's also a cut point. And so we're now at the step of analyzing the number line to see where second derivative is positive and where it's going to come out as negative. Definitely good stopping point for the moment, though. Any questions so far, folks, to this stage? Okay, and let me just fix this part of the notes. I don't think that needs to be circled any longer. So now that we have the critical number, the immediate next thing we go to is, for step 3, recall all we want is intervals where it's concave up, concave down. That's going to be resolved right here. We start at 0, put that into that same color purple from before. E power -1 is somewhere out here. Let's estimate it though, just to get a feel for what our test points should be. E to the power -1 is about a 0.37 if we're rounding really roughly. So let me put here approximately 0.37. That means we can select, say, a 0.1 again should do the job. And maybe a 0.5 or 1 would do just as well, up to you. We need to find the sign of the derivative in just 2 regions, here and here. And this is for f double prime. But notice we do have a set of expectations already. I would anticipate in this region, here to here, looking at the graph, should be concave down. And so I'm expecting the second derivative to be negative here. Hopefully the voice holds out for the next part. Here, it looks like it's concave up, so it should be positive. Pretty much what we're doing now is just double checking that really happens. Let's evaluate f double prime at 0.1. Where's that going to go? We'll put it into this whole thing right here. This is 2 natural log 0.1 plus 2 divided by 0.1. Back to the calculator. The calculator is getting a lot of use in this section, and in the next section it will as well. So 2 natural log 0.1 plus 2 divided by 0.1 gives us a negative quantity. So let's say down below, less than 0, which means less than 0 here as well. Again, the number is not as relevant, it's just the sign we care about. Then we'll do it again at a 0.5. Here it would look like this. You're putting in a 0.5 in those 2 locations, comes out as positive. That's not great for the notes. So let me put this also here in the notes, just as a paper trail. At 0.5, we got 2 natural log 0.5 plus 2 divided by 0.5. Again, we're inputting x into these locations for the second derivative. We came out as positive, so we'll say greater than 0. And greater than 0 here. So what does that finally mean? Our conclusion now is that f, let's say here, continues. I think the page break is unavoidable this time. F is concave down on this interval where it was less than 0. So that will be from 0 to e power -1 and is concave up on over here. This positive interval goes e power -1, doesn't ever stop being concave up, goes off to infinity on that interval there. Well, we've got it, folks. That's the situation of concavity. Again, it looks about right based off our visual inspection of concavity. Now, one thing I would have never guessed, if I would have said where's the inflection point, I'd probably say about right here. It just looks right. Nice number like 0.5. Well, that doesn't seem about right. That's the inflection point. Well, the first coordinate at least, e power -1 at 0.37. So the inflection point is really about here-ish. It's right there where it transitions from being concave down on the left to concave up on the right. That's pretty hard to spot. So now we can say, what's the inflection point? This is the step that's analogous to dealing with local mins, local maxes, but now it's about inflection. We want the full point, so we'll say first input e power -1, and it goes inside the function f. We have to evaluate f at that value, so let's go back up and grab the original function f. I keep forgetting what it was. So it's x natural log x squared, so this is going to turn into e power -1, comma, throw the same quantity in for x, e power -1, natural log e power -1, add other parentheses on the outside to square it as well. This is turning into a interesting parenthesis hell. But a good way to track them is I have 1, 2, 3 open parentheses going this way. So I need 3 closed parentheses going this way to match the delimiters. Just about there, the function does simplify in the typical way. There's a cancellation and the survivor is just -1. So this turns into the point e power -1, comma, let's see here, starting right here, e power -1, multiplying that -1 to the power of 2, but then that's a +1 times e power -1. So that's kind of another surprise in this problem. The first and second coordinate of that inflection point are exactly the same. I personally would have never guessed that. That's kind of an amazing coincidence in this problem. But because it's such an amazing coincidence, I would be suspicious. Let's see if it really looks about right. What's e power -1? It's about a 0.367. So I need to match that for first and second coordinates if that is the right value right here. So take a look. 0.37. That's kind of hard to hit unless I zoom in about. You know, that looks about right. At a 0.37, the next coordinate rounds to 0.37 as well. To me, that's a strong amount of numerical evidence. We are on the right track with this thing. Well, that's the end of this one right here, folks. And that's the full tour of everything we've been doing when we ended class last Wednesday. Just to add one last portion, this right here is e -1, e -1, the inflection point. Definitely a good amount of work to run through all that stuff. Any last questions or comments at all, folks? Okay, so this is kind of, in my opinion, one of the worst case kind of problems that you might have to take a look at in a web assigned setting. This would be too much of a quiz problem. This is like 2 problems at minimum. And this would never fly as an exam question. This is like several exam questions altogether, like a good, maybe a third of the exam to get through all this stuff. But think of this as good practice. Sometimes the problems get kind of long and nasty, and it is a skill to just keep on slogging through, try to check mistakes as you go. The next thing we're going to take a look at is the second derivative test. That sounds confusing. We just used a second derivative test. The one we used up here is for concavity. There's another second derivative test when it relates to local minimums or local maximums. And to explain how it works, we'll just reuse the last problem. That's recycling, I guess. Reuse, reuse, recycle. And here's how the test works. It says, well, first thing you have to do is find a critical number. And your second derivative has to be continuous at that critical number. This is more the technicality. I don't have any problems where that goes awry. But I do have a problem where part C does go awry. So step 1 is you find your critical number. Then you feed your critical number into the second derivative. And if that second derivative is positive, well, that means you're dealing with something that's concave up, like down here. And it also means you have a local minimum. So if that's a critical number, this is the local min, where f double prime at that critical number, it's concave up. So that should be positive. And we mentioned this a little bit on Wednesday's class. This is where I struggle a lot with mathematics, because when I see these directionalities, my mind just wants to kind of force them into something that makes more sense. But there's no fixing this. Bigger than 0 on the second derivative corresponds to a minimum. And you really just have to see it to believe it sometimes, or run through the proof. Likewise, if we look at this location, that's a local maximum, but it was also concave down, which means the second derivative is negative here. And so just to make that related comment, we have a local max where f double prime at the critical number where that occurred is, double check, concave down, so less than 0. So that's the idea with the second derivative test. And the good news about the second derivative test is, look at what you're skipping when it comes to local minimums, local maximums. If you decide to use this test, you skip all of this stuff right here. Well, you still have to solve, oh geez, where are we at? That's the example 2. Sorry, went way, way too far. You skip all of this stuff right here. And that's wonderful, because that is a lot of work to show, building out the number line with your critical numbers, testing the values and making conclusions. All that can be sidelined if you're using the second derivative test. Let me also delete that. That was just a visualization before we got to our conclusion. So we have just one last problem on these notes where we're going to give this a try on the second derivative test. And then when we go to the next section of optimization, we will take our first derivative test and this second derivative test, and we're going to fine tune them for not local minimums, maximums. We're going to change it around and make it be a test for absolute minimums, absolute maximums. So we'll see how that goes in the next notes. But first, we should practice this. So here's our practice problem for second derivative test. Any comments about the test first, folks, before we give it a try? Okay, the one thing we didn't discuss very much is this possibility. Notice it says then the test has failed. What we mean by that is not that the test is wrong, that it somehow should be stricken from math, it's illogical. What we mean is the second derivative test won't give you information about minimums or maximums. You now have to do something else if this eventuality ever occurs. This never happens with the first derivative test. It's a consequence of just the second derivative test. But other thing to mention is this test is excellent whenever f double prime of x is fast to find. It's going to say to calculate, but I don't have enough space to write that in. So in other words, if you had to do a quotient rule for just your first derivative, then you're going to do a quotient rule for your second derivative, this is probably not your best test. But if you're dealing with a polynomial, you mean I could get the fifth derivative on this thing pretty quickly, and I know you all can too. This is a wonderful situation for the second derivative test, because all the derivatives go really quick. So the process starts off like this. At step 1, you just start taking derivatives. Well, let me say that a little bit better. Step 1 should kind of focus on this aspect. You want to take a derivative and then find a critical number. Again, that's kind of our mantra for most of these problems since 4.2, 4.3. So start with f prime of x. Oh, and let's also fix the function. The function is h, not f. You have no idea why I put an h there, but I guess just to see what I would do. It should be h prime of x to match the notation. Then going left to right, we're going to get 15. X power 4 minus 15, x power 2. So we've done it, folks. That's our first derivative. Now we need to simplify this a little bit further for our purposes. We can factor out a 15x squared to start. So divide 15x squared for both terms, and we will get x squared on that term minus just a 1 on this term. Over here, Based on pattern recognition, you've probably noticed that's just another difference of squares, so we should factor that. It is now 15x squared, x plus 1, x minus 1. And that's now our first derivative. I would differentiate it in this format because that's a product rule with 3 different factors, meaning you'd have 3 different terms. If I'm going for the second derivative, I'd be using this one right here. But over here is great for equation solving. We set this equal to 0, and this would imply immediately 15x squared is 0, or x plus 1 is 0, or x, yeah, we have to move the window. I thought I was going to make that fit. Let's move that just a touch, or x minus 1 equals 0. Then the solution to all 3 goes left to right. 0 is the only solution on this first term, or excuse me, first equation. Then it'll be -1, then +1. So we've got our critical numbers. We'll say that these are the critical numbers of H. So that's our step 1. We have all the critical numbers. Now in step 2, it's focusing on this part, not the inequality. We just need the second derivative to work with the critical numbers. So in step 2, let's now calculate H double prime. We'll do it relative to that format of the second derivative, and we'll get 60x cubed minus 30x. So not too bad. We don't necessarily have to do anything further to this thing because we're not equation solving on it. We're not solving inequalities. All we're going to do now is take whatever the critical numbers were, it's those 3, plug them into the second derivative, and just see what the sign is, being very careful with our conclusions we make. So we're now at step 3. Very fast process after comparing it against the first derivative test. Just scroll just a touch. First, we'll do H double prime at, I guess we'll just go left to right. Let's do 0 first. When we plug in 0, well, we're going to get 0 here minus 0, which is equal 0. And then this is that bad outcome. We had a derivative equaling 0 right here, which means the test has failed. I'll put here that this implies no information can be given for H at 0. We have no idea. All we're doing is using the second derivative test. We're following that to the letter. I'll never make you convert to the first derivative test to investigate further. You would do that if you were just super curious and you want to do it on your own. But let's see what did happen on this. So we're just done on this step. Let's plug this original function in and just see what in the world is going on, because that's kind of mystifying in a way. Let me just put this in a better spot. So our function goes h of x. We're putting in the original function, 3x power 5 minus 5x power 3 plus 4. And right here at 0, that's our problem right there. That's neither minimum nor maximum. The function just keeps on decreasing in that kind of way. If it looked like this instead, if it turned up and that was gone, that would have been a local minimum. Or if the left part was wrong, that would say like that, and that wasn't there, that would have been a local maximum. But this is one of those cases where it's neither minimum nor maximum, just fully decreasing. We couldn't tell that from this information here. We had to use some other method, like graphing it, or the first derivative test would have revealed this to us as well. It just would have said decreasing and then decreasing again. So, well, that's one down. We go back over here and just do it again. H double prime at -1. This will be equal to, now where's our H double prime? It's right here. Throw -1 inside there, and we get 60 by -1. Since -1 cubed is -1. Then it'll be plus 30. since a -1 here will force it to be positive, and that means we get -30 altogether. That means we're in this location. Let me change the colors. The color coding is actually going to break down, but let me do it this way. We just got negative, and so we found a local maximum. And I think right here is a good spot to put your conclusion as well. So step 3 is going to also have the conclusion. I would just say right arrow. That just means less equation implies h at input -1 again. If we're putting -1 inside, we're just throwing that right inside here with a -1. You'd probably do it this way though. Either use Desmos, h at -1, and it gives us a value of 6. But let's do it like if you were doing a real exam question. You probably would type it into your calculator like this. 3 -1 power 5 minus 5 -1 power 3 plus 4 gives us the value of 6. So we have an output of 6, and we get to say is a local maximum. Double checking the graph, because it's good to check as you go. If you put in -1, yep, right at -1, we have a local maximum at height 6. So everything is checking out so far. Any questions, folks, with that first conclusion here? Okay, I'm right at the colors for color coding. I'll just use the pencil tool to correspond how we made the conclusion from up here down to here. Then one last one to go. See if I can zoom out. That's too much zooming out. Let's keep it at 130 and do H double prime at the last critical number, +1, way out here. So this time put in a 1. If you did that, the 1s just drop out. 1 to the power 3 is just 1, and you get 60 minus 30 for a value of now +30, which is greater than 0. I do want to squeeze one extra thing over here where my -30 was. I want to convey less than 0, just to remind us that we were looking at that part right there. Sorry, I should have included that earlier. Over here, we have greater than 0, and that means we're looking at this region. Let's use a different color. How about that to work? So now we can say that this implies h at +1. H at 1 is faster to calculate. We get 3 minus 5 plus 4, so 7 minus 5 for a value of 2. And this one is a local minimum. I'll just say min for short. And a light blue box just to convey where we grab that conclusion from the test above. Then again, if you're doing this as a web assignment problem or a quiz problem, any graphing calculator is really helpful for this, just to check your work as you go. We put in a 1, we got a 2 as a local minimum, and yeah, that looks about right. It's a local minimum visually from our 4.1 work, and the 1 is the first coordinate, 2 is the second coordinate. 2 is the answer, what you would give WebAssign, for example. Well, that's how the second derivative test goes. Again, we like the second derivative test only because it is sometimes extremely fast. Unless your function looked like this, if h of x was something like 17 natural log 3 divided by e to the x, that's a horrible function to work with, but the second derivative test is going to be way, way worse than the first derivative test, because you're going to have to do a lot of work just to even get to the second derivative test. Or excuse me, just to get to the second derivative, where all the analysis happens. But we did it, folks. This is local minimums, local maximums. Any questions at all, folks, with what we've done so far? Okay, well, let's take a look at what we have for time. We've got about 20 minutes. I think that's just enough time to take a look as a preview of the next section. We won't try to get too far, but let's see what we're getting into. Let me save the notes right here just to make sure that does happen. Good little mental break for us while Microsoft Word struggles through this. And now finally, here's our section 4.2 on optimization. We're skipping section 4.3, which is a technical section on limits through L'Hopital's rule. But the bigger takeaway is, or the bigger thing we want to get to is optimization. And here's one takeaway we should take a look at right away. Let's see if we can compare these side by side. That's kind of tricky sometimes. What I want to do is display the second derivative test, because we've made a change to it, against the old one. The old second derivative test says, if you have these conditions pass, then you have a local minimum or a local maximum. But now, here's the new test. If you have that, well, you have a critical number to start, and the second derivative is positive, sure, it's a local minimum, that's the old test. But here's the new part, highlighted. If the second derivative is now positive for every single value of x, we're saying concave up always. That means the curve has never a possibility to turn down to make a minimum occur. Then FFC is in fact not just a local minimum, it's an absolute minimum as well. Likewise, if the second derivative is negative, not just for values nearby the critical number, but for all x in the domain, then you have an absolute maximum. So another takeaway that's hard to see here is, let me see if I can zoom in just a little bit more. Notice on the old second derivative test, with its local minimums and local maximums, what you're doing is testing the sign of the derivative against the actual critical number c. But if you're dealing with absolute maximums, absolute minimums, you do not put in the critical number. You're looking at the sign of the derivative for all x. You have to show it's always positive, not just at the critical number, everywhere. And same for part B if it's minimums. So that's a heck of an adjustment. And aside from all that stuff there, let's see what we can do with the problem down below. Now, I want to be real upfront with you. Example 1 is silly. Because we're looking for two positive numbers to maximize the sum of cubes, the strategy is just to divide this by 2, and you have the answer. It's 7.5 twice for both numbers. The reason we're doing this silly problem is, think of it as we're building towards these problems where there's no fast way to get through it, and we're going to use the same kind of strategies. So we're trying to solve these ones down the line. I have 3 problems that look about like these things. One's a rectangular box we're going to try to maximize or optimize. Other one looks like it's pharmacokinetics. We're going to optimize on blood alcohol levels. But to get a feel for all of those, it's good to work with a silly problem just to see how things go in something that's more simplistic. So let's see if we can get started on this one and how far we'll get through. First thing I would focus on is this statement. The sum of two positive numbers is 15. Already we've indicated that there's 2 unknowns in the problem, and we could say let x, y be the 2 positive numbers. Then from the statement, the sum of them is 15. We have a constraint equation that says x plus y is constrained to be 15. We think of that as a constraint because, well, x and y being positive is pretty wide open, but they have to satisfy this one condition. Now they ask us, what is the smallest possible value of their sum of cubes? So in other words, we want to, because it said smallest possible value, minimize. It's a sum, so we're adding things together. It's a sum of their cubes, so we're cubing x and y. And that's the thing we want to make as, let's say, smallest possible value. We want to make it as small as it ever could be. So, well, we've got an equation on the left, an equation on the right. And the big trouble with all of this is they all depend on a function f, which involves just one variable, either x or y. So our next strategy is we need to take the thing that we're going to optimize. The thing we're optimizing is the thing they tell us to minimize or maximize. So take the thing you want to optimize and write as a function of one variable. If it's in as two variables, this is really a calculus 3 kind of process, multivariable functions. We need to eliminate that and work where we really belong, one single variable. That's the constraint equation that makes it happen. You could eliminate either variable. You're going to get the same answer either way. But I feel like, for me personally, I would try to eliminate the y value because I'm used to looking at f of x rather than f of y. So if we're going to try to eliminate that one, that's not a great color coding in this problem, we'll just go over here and solve for y. Will be y equals 15 minus x, and this value right here is going to go in place of y in that location. The moment we do that, we now do have a function of f. We can now say f of x equals x cubed plus y cubed, but y is now just as good as 15 minus x. So we have now a function. The constraint equation is pretty much done at this point. We now know we're minimizing this thing. And it's at this stage that, I'll delete this for the moment, but I think this is good to emphasize. The entire strategy in section 4.4 is to get to here and make it a 4.2 problem. That way you're doing the same exact steps you were doing in the prior section we just finished. So our goal is to abstract away from everything and get down to that function there. Now that we're there, we need to pick a method. The first derivative test can be used, or the second derivative test. I put here, show all steps using the second derivative test, only because that's a function that's not hard to differentiate repeatedly, and so second derivative test would be the easiest on this one. Well, any questions or comments, folks, to this stage? Okay, let's call all of this step 1. And the major purpose to step 1 is to find the function that we want to optimize. We're using the second derivative test, so let's take a screenshot with it and move it down as we go. And now here is step 2. That looked kind of weird. Let's call this step 1. And here is step 2. So now we've got that function f. We're at this stage, highlighted in yellow. We need the critical numbers, the critical number or numbers to that function. And that's found by doing the first derivative. So calculate f prime of x. It's always good to make that prime a little bit more visible so we don't conflate it with the wrong function. And it's not so bad to start. First, we will get 3x squared. Then it becomes a chain rule, but we've looked at a lot of these as chain rules. Let me know how this goes. If you feel you've got lots of practice with a chain rule, you might start writing it down like this. Outer function is power 3, so just go 3, power 2. The inner function is 15 minus x, so it goes inside here. And it goes right over here as a derivative. If you put a -1 right here, I'd say good call. That is a good shortcut to take. Not great for the notes, so I'll usually show this step in the notes. That look all right to folks as the chain rule from this portion? Okay, if we feel happy about it, let's now go into the next step. Still, we're working on the first derivative, f prime of x, and it's now equal to 3x squared plus 3 times 15 minus x to the power of 2. Derivative right here is just going to turn into a -1. So there it is, our -1. And because we're trying to solve an equation, this power 2 is not very kind to us. We actually need to expand all that out, combine our like terms, potentially factor or do whatever we have to do. So let's start by writing down, copy 3x squared to start. I put plus, but that was a mistake. Let me try to fix it again. There's a -1 here, multiplying to 3. So I'm just going to lead with -3. Then from here, let's expand out 15 minus x squared. We could do it in the margin if we like. 15 by 15 is 225. It'll be -15x minus 15x and then plus an x squared. So combining the like terms in the middle, we're gonna get 225 minus 30x's plus x squared altogether. And geez, 3 by 225 sounds like negative 625. So that's our next step, distribute the 3 in, the negative 3 in. So 3x squared minus 675, thank goodness no carry with that one, plus 90x minus 3x squared. And this was a coincidence. We have an algebraic miracle where the degree of our equation has been dropped by 1. X squared is eliminated. That means the step in yellow of finding f prime of c equals 0 is going to be far easier because this is now a linear function. Negative 675 plus 90x. We set it equal to 0, and now we're looking at that step right there. So, well, it's not too bad. Coming back over here, let's go methodically with this one. Add 675 to both sides. 90x is now positive 675. Next, divide by 90. And I think that's where my arithmetic abilities completely end. Let me use a calculator on that one. 675 divided by 90 goes evenly 7.5 times. So x equals 7.5 is the critical number of f. So we're very, very nearly there, but we still have more work to do because finding the critical number is never enough. The reason for that is, well, if you look at, oh, do I still have it? I think I lost it. It was this function right here. Let's put it in one more time just to emphasize this issue here. H of x was 3x5 minus 5x cubed plus 4. And we said right at 0, we did have a critical number to that function. But it turns out right at 0, that was neither a minimum nor a maximum. This is the reason why in section 4.4 it says, show all steps of the second derivative test. Because the critical number is actually not enough. We have to verify that at the critical number, there is really a minimum. It's not a guarantee at all in these kinds of problems. So there's further steps. And that's where the second derivative test is going to start taking over for us. Wow, we still have some time. I think we might be able to finish off this problem. Here's step 3. Now in step 3, what we're going to do is take our first derivative in its most simplified form. It's right here by the red dot, and just differentiate it again. F double prime of x is the negative 675 is gone now, it's constant. The derivative of 90 times x is 90. And now this is the moment where we have to look at this portion. The second derivative has to be positive for all x in the domain of f. And you know what? It is. X doesn't even enter the picture. Any x you pick, we get positive. Let's emphasize it's bigger than 0 for all x. Bigger than 0. I said x bigger than 0 because our problem said x's and y's were positive numbers to begin with. So there was a domain restriction on x. But because we got bigger than 0, we have an absolute minimum value. It's going to occur when x is 7.5. And so here is our step 4, the conclusion. By the second derivative test, f evaluated at this right here, the critical number, 7.5, which is now equal to, well, it's going to be our absolute minimum, but we now need to find the original function f. Where was it? It was right up here. So that'll be 7.5 cubed plus 15 minus 7.5 is 7.5. So that's kind of the easy part of this problem. We kind of knew what we were expecting to start. So 7.5 cubed. Now let's go back to the calculator. We have really just 2 times 7.5 cubed. We combine those like terms. And it minimized at 843.75. And that is the absolute minimum sum of cubes in this problem. The reason it worked, the reason we can say absolute minimum is because of that part right there. If we can't establish that it's always positive for every single x in the domain, then maybe we shouldn't use the second derivative test. If that's a hard inequality, probably the first derivative test should be used instead. But we did it, folks. We've optimized. Sure, it's a silly problem, but think of this as good practice before the problems get a little bit harder to work with. Any questions at all, folks, with that whole process? Okay, so optimization is sometimes considered one of the most important applications of calculus, and that's exactly what we're hitting right now. When we come back on Wednesday's class, we're going to try this again, but we're going to reformulate now the first derivative test, and it has the same kind of idea. We want to show the sign changes for all x less than c, and it changes to this other side for all x bigger than c. It's about those for all x's, which are giving us an absolute maximum or an absolute minimum. So that means if you're using the first derivative test, there's exactly one critical number, and the sign has to only change to the left and to the right of that number. That's a good function or a good test for this thing, because the first derivative is hard already. The second derivative is way harder, and establishing that part of the second derivative might even be the hardest thing about this problem. This is a good one for the first derivative test. So we'll give that one a try on Wednesday's class. Any last questions or comments, folks, then, before we call it a night? Okay, well, I appreciate everyone's hard work. I know that this is not the easiest section, but we're nearly through with it. Once we finish off this section, we're going to start changing over from differentiation to integration. And section 4.5 will show us how to make that work. But have a great night, folks, and we'll see how all that goes on Wednesday's class.